Tetris is a game with a colorful history, and its entries on the Famicom NES platform are no exception. The first-party release feels like a perfect candidate for behind the code, as it has odd behavior at times and even hidden features that are worth examining. What do I mean by hidden features? Well, it's a one-player game, but enough code was written and left in the ROM for a functional two-player option. You can unlock it with one Game Genie code. While this is an interesting bit of trivia, the focus of this video is the code responsible for crashing the game. Some would deem a crash as a failure, but others in the Tetris community consider it a victory, an attempt to crash the game as soon as possible. What causes the crash to occur? We're going to find out, and it all begins with counting. Have you ever given much thought to how we count? Probably not. We learn how to count at a very young age and just accept it. But think about it for a moment. 0 to 9 and now we're done. That's it. No more unique symbols remain to represent numbers. Now what? Well, we start over. We start over with 0 and increment a new column to the number 1. Boom, the number 10 is born, a number created using 2 digits. We keep going as long as necessary, rolling over individual columns to 0 and carrying 1 to the next column when needed. Programming the NES is the same way. Instead of single columns, we work with groups of 8 bits at a time, called bytes. If we add two 8-bit numbers together and can no longer hold the result inside a single byte, the processor sets a flag that indicates a carry occurred. Programmers can then add that carry to a second byte and continue counting. Now we are using up to 16 bits to store a value, but we still have to handle only 8 bits at a time. So we take the same approach for counting in binary or hexadecimal. Eventually, we run out of unique symbols and start over in a new column. Now, we may wish to show a value we maintain, like a score, to the player so they can see it. We want to move from a value stored in one or more bytes to graphics. But a player doesn't want to see a score of 111001001 in binary or 1C9 in hexadecimal, the way a processor would see it in a manner of speaking. Players want to see 457. At some point, a conversion needs to be performed so we can pick out the correct symbols for a base 10 numbering system. When is the conversion performed? The programmers of this NES Tetris elected to maintain the score value in RAM as decimal by performing a conversion each time addition happens. For example, if 9 and 3 are added together, the result is 0C in hexadecimal. Additional logic sees that the low column, called a nibble, is in the range of A through F. It therefore adds a value of 6 to roll us past these 6 possible letter values of hexadecimal. The result of this is technically 12 hex, but really, we now have the appropriate pair of decimal digits, a 1 and a 2, stored in a single byte. The graphics logic only needs to split each byte into 2 nibbles and find the tile with the appropriate digit to build the score on the screen. Our maximum displayable score in Tetris is 999999, so the game uses 3 bytes. The code to add to the score when pieces land or lines are cleared looks like this. 5 of the 6 places require code for conversion. None of the line clear scores have a value other than 0 in the ones place, so we never have to worry about converting that one. Yay. We roll through the logic and check the tens place, hundreds place, thousands place, 10,000s place, and 100,000s place. We are adding a new score and converting each place to decimal as needed. It works and it isn't too bad. But things come off the rails thanks to an important component in scoring. The score you receive for a line clear is different depending on how many lines are cleared at once, 1, 2, 3, or 4, a Tetris. The score is looked up from a table contained in the ROM. After each level up, the total score you receive per clear also increases. The calculation is your current level plus 1 times the appropriate value from the lookup table based on the number of lines you just cleared. So if you clear a single row on level 3, your score is 4 times 40, 160. 160 must be rolled into the 3 score bytes manually. Seems simple enough. However, there is no multiplication instruction available for the processor of the NES. Uh-oh. Instead of calculating 160 via multiplication and then adding it to the score, we have to add 40 to the score 4 times by using a loop. The higher your level, the more times we iterate through this loop when scoring a line clear. As you know, we aren't just adding the same number 4 times, we also check for A through F on each decimal place and perform a conversion when necessary each time we do an addition. Despite the fact this is horribly inefficient, Programming elected to use it under the assumption that no player could ever reach a level high enough where scoring logic becomes a problem. There is code that recognizes that the score has maxed out and sets each of the 3 bytes to 99. Unfortunately, there is no code that checks to see if this maximum has been reached before performing addition. So the game continues to waste time doing addition and conversion even after the maximum score has been reached. Also note, this scoring logic is performed whenever a piece lands. It adds 0 to the score each time through the loop. At least conversion logic isn't required, as the score never changes. Now, in previous episodes, we've seen what can happen when game logic for creating the next frame doesn't finish before it's time to draw that next frame. Some games output the most recent frame again so the CPU can finish the next frame's work. It stalls the graphics update, among other things. The game slows down. Other games don't care if the next frame isn't ready, they just perform their updates. This may result in some sort of artifact, such as glitchy graphics. Tetris would seem to be of this variety, but unfortunately is not limited to some graphics corruption when the CPU runs out of frame time. Oh, but have no fear, the graphics will eventually go bonkers as well. Perfect fodder for a future episode. So what's the worst thing that can happen? There is a possibility that Tetris will crash the processor of the NES if it doesn't finish the next frame's work within the allotted time. How does this happen? This journey is a wild one. Let's go. Here we have Tetris running innocently in an emulator. We're going to analyze and illustrate numbers and logic that are happening behind the scenes and pair them with the gameplay window. If you love metadata, fasten your seatbelt. We spoke earlier about how player score is maintained in a decimal format in RAM. Well, a couple of things that are not maintained in the same manner are the level and lines indicators. As we progress further in the game, these values aren't translated to the screen very well. Level uses a lookup table to convert from hexadecimal to decimal, but the table maxes out at 29. So, data from outside the conversion table, meant for other things, is used on screen after that. Line logic does a partial decimal conversion, similar to the scoring logic, but only for the lowest 2 digits. 999 lines will therefore roll over to 100, and so on. Because of this, let's use a Lua script in the emulator to show the proper values inside an overlay. Since we need to get really far in the game and don't want to have to play it, let's use a Tetris AI script to handle gameplay. I'm a programmer, not a Tetris master. With those basics complete, it's time to get fancy. The PPU draws the graphics to the television screen from top to bottom. It does this for every frame. This is how video output works. The area between the frames is called vertical blank. During this time, the PPU doesn't have to output any graphics. It uses a non-maskable interrupt, or NMI, to signal the CPU that, hey, it's time for graphical updates and stuff. This happens every frame. The CPU then stops what it's doing and executes a designated handler for NMI logic. Once it finishes the logic, it resumes its regularly scheduled programming. This is quite literally clockwork. The window we see right now is called the event viewer. It's a timeline. It illustrates not only the time the CPU draws graphics to the screen, but also the vertical blanking area. Since the CPU is working on the next frame at the same time the PPU is drawing, we can place boxes on the screen to indicate when in time the CPU is executing specific things. Let's return to our code that rolls up a line clear score into the total score. The start of that scoring loop is here. That will be the moment we mark on the event viewer timeline. If we clear a line or simply land a piece in the game on level 0, a box appears for the scoring loop. Level 0 means 1 pass through the loop. If we clear a line on level 10, that clear means 11 passes through the scoring loop. Now we start to see scoring take up a larger chunk of total frame time. Speaking of frame time, allow me to mark a few additional CPU moments in the event viewer after a line clear occurs. We now have a box for when the scoring loop ends and therefore know the total execution time for that loop. We also have this large chunk of repeating boxes at the bottom before NMI. What are those? Additional logic is executed after scoring, and then the CPU is put in an infinite loop to wait on the NMI signal from the PPU. The CPU is wasting time here. We have a box for each time it goes through the loop in the wasting time code. As the game level gets higher, the score logic takes longer, and the CPU has to wait less and less time for NMI to occur until finally that NMI will begin to interrupt additional logic after scoring that the CPU still needs to execute before the next frame. So, the interrupt for sending next frame data occurs, the logic for the interrupt finishes, and we are returned to do whatever is remaining in that post-scoring logic. Under ideal circumstances, interrupting remaining CPU logic for a frame never happens. Realistically, it probably happens for most NES games. For this reason, code is written to handle the situation. This may result in lag frames, but the key point is that logic is aware that the situation can happen and handles it. Tetris doesn't really care. It was written under the assumption that this would never be a problem, or if it did become a problem, it wouldn't result in anything bad happening. Using a single freeze frame to illustrate score execution time works well, but it would be nice to log this illustration as a number so we can let the game run without the need to pause each time we want to see score performance, especially after the score logic spills across 2 video output frames. So, to numbers we go. The NES runs at a frequency of 1.789773 million cycles per second, called megahertz. Do a bit of math and we see that a single frame of video lasts about 29,780.5 CPU cycles. Our score calculation for a line clear is going to take some percentage of this, and it will certainly take much more time at level 50 versus level 0. How do we know how much time it takes? Each instruction executed takes so many cycles to complete. We'll calculate the number of cycles consumed for scoring by noting our CPU's cycle count before loop execution begins, and then after all loops have completed. Subtracting the former from the latter will give us the cycle count for our line scoring logic. We'll place that value here, and use the number to calculate the percentage of frame time that scoring logic consumed. The bracketed number is the number of lines that were cleared. Beneath that, let's show the cycles required for adding a score of 0. This will update each time a piece lands without a line clear. As the level increases, so does the number of iterations through the scoring loop. Naturally, we see our cycle counts increase inside the overlay. Scoring a line clear on level 67 requires around 20% of frame time, yet the CPU gets its work done and still wastes about half a frame's time waiting for the PPU to interrupt via NMI. Let's keep going. Eventually, our score approaches the maximum. The level on which this occurs will vary, as clearing a higher number of lines results in your score increasing at a faster rate. Once our score hits or clears 999999, additional logic is executed to place 99 in each of the 3 bytes, and this adds 11 more cycles per loop iteration. The percentage of execution time for the score loop sees a notable increase because of this. All line clears after this point are still scored and added to the maxed out score via many loops. At this point, line clear scoring needs almost a third of total frame time. Eventually, the score loop will dominate so much of frame time that not only will the CPU not need to wait for NMI, that interrupt will occur in the middle of additional work that the CPU still needs to do. The consequences of this happening will vary depending on which logic operation was interrupted. In some cases, nothing will seem to happen. In other cases, an absolutely amazing cataclysm of unfortunate events will take place. And that's what we're here for, isn't it? We've talked about NMI interrupting current CPU logic in many past episodes of Behind the Code, as well as this one. One detail we haven't covered is the important logic that takes place at the moment NMI occurs. This will help us understand the crash. If we jump somewhere else in code to handle an interrupt and then return from the interrupt, how do we get back to what we were doing, to where we were before the interrupt occurred? Various CPU registers are required to answer these questions, so let's include them at the top. These values are stored inside the CPU and used to assist with execution. Highlights include the program counter that keeps track of where we are executing code by storing the 16-bit address for that code's location. This in mind, we need example code, so let's use the infinite loop code the CPU executes when finishing the next frame's work with time to spare. The program counter in this example will jump back and forth between AA37 and AA39 as it continues to waste time. That code loads the value of this vertical blanking or VB interval flag from RAM into the accumulator. The value is 0, so the accumulator is 0, and the 0 flag is set. This BEQ instruction beneath it is set to branch back up to VBI check loop as long as the 0 flag is set. There's our infinite loop. Hey, load this value. Is it 0? Yes. Okay, branch up here. And do it again, forever. I'll fill in a few other values for the sake of accuracy. They aren't very relevant for the specific code we are executing, but these are real values from the emulator when we reach this point in code. That said, this large box doesn't contain everything. I've intentionally omitted some items for readability. So let's say this loop is executing and inimi occurs. What happens? Well, the CPU does a few things for us. It takes the program counter from the address we are leaving and places it on the stack. The PC is 16 bits. We work with 8 bits at a time, so the high byte goes on the stack first. The low byte then follows. The CPU saved off where we just were. Next, it takes status flags, including negative, overflow, interrupt, 0, and carry, and pushes them to the stack as a single byte. There are a few more bits to this byte that we won't cover here, but the point is that we store these flags on the stack for safekeeping, just as we did the program counter. The CPU is basically saying, here, hold this. Oh, and this too. With these 3 bytes stored on the stack, the CPU jumps to the designated address for handling inimi. Naturally, the program counter is set to that address, which in the case of Tetris is 8005 hex. From there, it can do inimi stuff. Eventually, it will return from interrupt with RTI. Obviously, the CPU wants to know where he was and what he was doing. So, it pulls the first byte off the stack to restore the status flags to what they were, and pulls the next 2 bytes off the stack to know where to go in code. That's how we resume execution after the interrupt. Shout out to the CPU and the stack. Oh, and by the way, one of the last things the inimi code does is write a value of 1 to the VB interval variable in RAM. So when we resume execution here, the loop logic loads a 1 into the accumulator. 1 is not 0, surprise, and we fall out of the infinite loop. While it is nice that the CPU takes care of this for us, it is the bare minimum. What about the accumulator and the X and Y registers? Surely they were changed multiple times inside the inimi handler. They can't be the same as they were when executing this code back when the interrupt occurred. If you examine the interrupt handler, you'll find that programming elected to write code that pushes these 3 items onto the stack just like the built-in functionality did for the program counter and status flags. Naturally, the code immediately before an RTI to return from the interrupt will restore each of these 3 items. This returns us to a previous state that is much more authentic, and Tetris is one game that does this. Unfortunately, Tetris also uses RAM addresses 0 and 1, among others, as spaces to hold temporary values. This includes temporary pointers. So long as inimi interrupts during the infinite loop, these values aren't important. But that isn't always the case, is it? Some of you already know where this is going. Tetris, like many other games, has a jump handler subroutine. This subroutine uses the aforementioned RAM addresses 0 and 1 to hold the destination address for a jump to somewhere else in code. It is executed for various operations each frame. What happens if we are in the middle of executing this routine when our interrupt occurs? The code executed inside the inimi handler also uses RAM addresses 0 and 1, and it does not save off their values before it starts work, like it did the accumulator and XY registers. If we return to the jump handler after an interrupt and these addresses do not hold the same values they did when the interrupt occurred, where are we going now? Let's find out. I've modified our Tetris script so the console window reports any returns from inimi that do not land us inside an infinite loop. Naturally, this box lights up once the line clear score loop begins to consume too much frame time. What we want to see is an inimi occurring while we are inside the jump handler. That should trigger the crash. The reports coming in show the number of lines cleared just before the attempt, what level we were on, what the frame number was, the exact address of the logic we were processing when the interrupt occurred, and a loose description of what the logic in that area does. The earliest possible crash can occur when clearing a single on the transition from level 154 to level 155. However, the AI cleared with a double. Not only does that prevent the crash from occurring, but scoring a double at this level doesn't even consume enough cycles to interrupt remaining frame logic. We just managed to reach the infinite loop for wasting time with that double clear. So we keep going. Eventually, we clear a single line on level 157 and the game crashes. We interrupted the jump handler while at address AC8E. Let's check it out. Sure enough, we had started to work with addresses 0 and 1, named temp0 and temp1 in this code. The interrupt occurred here at the aforementioned AC8E address, which is right in the middle of the handler. This line underneath the jump handler report shows the address for the line of code that called the jump handler. how did we get here in the first place, as well as where we were in time when that call occurred. Scanline 240, PPU cycle 225. That would certainly be just before vertical blank occurs. The most important component, where did we go for code execution? Address 7F in RAM. There's nothing wrong with executing code from RAM so long as that RAM contains code. We've seen The Legend of Zelda load code from ROM to cartridge RAM and execute it. Heck, placing code in RAM is how the Famicom disk system works. But for Tetris, code is not what is stored inside the 2K of internal NES RAM. The same is true for most NES games. Tetris stores your piece location, level, score, controller input, etc. inside this range. The processor doesn't know this. It jumps execution to the provided RAM address and treats the values it finds here as instructions. 05 here at address 80 hex is exactly that, a value of 5. However, since the processor is executing this as code, 05 means execute an inclusive OR instruction. So that is what it does. I have this emulator set to break on CPU crash, but not to break on unofficial opcodes or BRK instructions. That said, I assumed that it would crash on the STP instruction here. STP is perhaps considered an invalid opcode in this version of the emulator. Future versions of Messen may change this specific behavior. One way or another, we crashed. If you're interested in more details on things you probably don't want to do with the 6502 processor, you may wish to check out this write-up about illegal opcodes. I'll provide a link below this video. The behavior we experienced is how the emulator was designed to respond. A crash occurred on bytecode E3, which is instruction ISC at address 85 hex. As for Tetris, is this it? The game crashes on level 157? No, there is so much more. In fact, it's possible we can get all the way up through level 255 and roll the game over to level 0, provided we manage to clear several crash hurdles along the way. But that endeavor requires its own video. Please like, subscribe, and share this video if you enjoyed it. I also have a Patreon available if you are interested, and thanks for watching.